Okay, so today I'm going to be making a brief explanation on finding the inverse of a matrix through uh, through row operations and using an augmented matrix. So, first of all, we got to understand what an elementary matrix is. So, an elementary matrix is a matrix that can be obtained from the n by n identity matrix I by performing a single elementary row operation. So, you know what I looks like? It's 1, 1, 1 along the diagonals, or it's ones along the diagonals for whatever the dimensions of the matrix is. It could be 4 by 4, 2 by 2, 10 by 10. But anyways, all the other entries are zeros. Um, so that's kind of our base matrix. It's almost like, think of like a 1, but as a matrix. It's multiplicative. If you multiply it by another matrix, you get the same matrix. So, okay, so our first theorem here is that row operations as matrix multiplication, if the elementary matrix E, which is just an elementary matrix, results from performing a row operation on I, and if A is an n by n matrix, and the product of E and A is the matrix that results when the same row operation is performed in A. Okay, so that's a long explanation, but basically all that it's saying is that when you multiply E and A and the matrix E, which is the elementary matrix, which is just like a changed identity matrix. So it could be 3, 0, 0 along the or 3, 1, 1 along the diagonal. If you multiply that by some matrix A, that's the same thing as doing a row operation. It would just be the same as multiplying the first row by 3. So both are interchangeable is what they're trying to say. Okay, so here's some more equivalent statements to back up what I just said. So first of all, theorem 1.5.3. If A is an n by n matrix, it is also true that A is invertible, B, AX equals zeros has only the trivial solution, C, the RREF form of A is identity matrix, and A is expressible as a product of elementary matrices. So basically this is saying it that if A is a square matrix, so n by n, it has to be invertible. Then, if it is invertible, then that means, or if not all of those matrices are invertible, by the way, but if they are invertible, then that means that the RREF form of A is the identity matrix. You can get it down all the way to ones along the diagonal, and then you'll have your solution matrix B. So then that also means that A is expressible as a product of elementary matrices, because in order to get it in our REF form, we have to use row operations. And what I just said in the previous slide is that row operations are equivalent to multiplying by elementary matrices. So to find the inverse using the identity matrix, we want to reduce A to the identity matrix, right? Because if we multiply A by its inverse, we should get the identity matrix. It's the same thing as imagine multiplying 6 times 6 to the negative 1, the inverse of 6. You will get 1 every time. It's the same thing with matrices. Hold on, sorry, having some mic issues. So if you multiply any matrix by its inverse, you'll get the identity matrix. So our augmented matrix is essentially going to be our matrix A next to the identity matrix. Then we just perform row operations, which are, again, multiplying by elementary matrices. And then after we do that, we'll get the identity matrix on the left, which was the former A, like our former matrix. Then we'll have the new matrix on the left, which is the inverse. So that is a way using row operations to find it. So you would just do row operations on A originally to find the I, which is the identity matrix on the left. And then once you do that, the row operations will carry through on the right, and that I will become A inverse. So this is the same thing as using matrices to multiply, except you're just using row operations. So here's an example if you want to pause the video and go through it. So try doing a 2 by 2 to start off. So you could do this using theorem 1.4.5, which basically just says it's 1 over AD minus BC. So it would be 1 over 10 it would be 1 over 10. It'd be 1 over 10 minus 12 times the original matrix. But instead of it being the original matrix like you see in the start, you flip A and D, and you take the opposite of B and C. For a 2 by 2, that will work every time. Except the only thing is, if his AD minus BC is 0, because then it becomes 1 over 0 as a constant in the front, and that doesn't exist in our terms. So then if we want to use theorem 1.5.1, if we don't want to use that, we set up the matrix 2, 3, 4, 5, and then we put the identity matrix by it. We use row operations, and we get the exact same thing on the right. So just showing it works both ways. Now try to do it with a 3 by 3. It's a little more complicated, but here are the row operations if you want to get through it. You could pause the video and try it yourself. But when you go through it, you obviously set up the augmented matrix, like we said, the A on the left and the identity matrix on the right. Then you go through a series of steps, so row operations, just multiplying by elementary matrices. That's why it works, because you just are multiplying by matrix on both sides. Then once we do this, we get a new matrix on the side. Once this is completely an RREF form, which I covered in the last video, by the way, if you don't know what that is. And this new matrix is going to be our A inverse. And if you want to check that this really is A inverse, you can multiply by this by A, and you will get the identity matrix. Okay, so if you want to check your knowledge on some of this, you can pause the video and try these problems right now. They're good. Okay, moving on. So here are the answers. So once again, if you let's say you get done with a problem and you're not sure about it, maybe the numbers seem too big or weird, or you just think you might have messed up, you can always check by just plugging in your calculator and multiplying back, or you could do it by hand. But when you multiply back, you will get the identity matrix. If you get anything else, it's wrong. Okay, thank you for watching. Have a good day, and recommend any new videos you want me to make.